Hey guys, welcome to another wonderful day of chemistry, and today we're going to be talking about the difference between single bond compounds and double bond compounds. And we're going to practice some double bonded Lewis dot structures. Here's what I want you to do is for F2, which is fluorine, you could probably figure out that the number of valence electrons in each atom is 7. And you could probably figure out the total number of valence electrons if each fluorine has 7 is a total of 14, right? And then kind of using that information, we can create the structure that looks like this, where we have two Fs, each one with 6 dots around it, and a single bond. What I want you to do is go ahead and go through that same process. Let me kind of show you it again. First, kind of write out, sorry, you're going to do this process, the same process for oxygen. So let me show it again. First, you're going to tell me how many valence electrons each one has and draw those. Then you're going to show me the total number of valence electrons. And then once we have that kind of framework done, we'll work on drawing a Lewis dot structure. So go ahead and do those things. Great. Hopefully you found by looking on your periodic table that oxygen has a total of 6 valence electrons. Hopefully you drew those two oxygens out. So if each one's got 6, that means we have a total of 12. So there's my 6 there, and a total of 12. Now, what's the Lewis dot structure going to look like? That's the question here. So, according to the rule is kind of draw each atom, give each atom the number of electrons, and then start with a single bond. So let's go ahead now, and we're going to draw a single bond right here. Boom. Now you'll notice that I'm kind of describing what's happening with the electrons, the valence electrons on the left here, or sorry, on the right, and I've got a total of 7 valence electrons. 7's not 8, so it's not balanced. So you might be thinking, well, what can we do to make it balanced? Well, this is where the idea of multiple bonds comes into play. So what we can do here is we can actually draw another bond between these two lone dots, and that's going to give my electron on the right now a total of 8. It used to have 7, now it's got 8. And then on the left, it's also got 2, 4, 6, 8. This drawing's a little bit sloppy, so let me go ahead and clean it up. Boom. Now it's nice and clean. You'll notice that it looks like almost like an equal sign kind of between these two oxygen atoms. Both the bonds are the same length and they're both kind of in the middle there. That's what a double bond kind of looks like once we're done. But sometimes when you're first trying it out, it might look a little sloppy. So make sure that as for your final answer, you kind of clean everything up so that it's nice and neat. Awesome. That's how you do multiple bonds. You kind of make a single bond, realize a single bond isn't enough, and then you do a double bond. So before we get any further in this, what I want to go over is some vocabulary, and we should have talked about this already. The difference between the two red dots up here and this blue line with the 2 dots next to it. These 2 red dots are called a lone electron pair. It's just 2 valence electrons that are not in a bond. Versus this blue thing over here is called a shared electron pair, or sometimes we refer to it as a bond. And so keep in mind that if you have a line, that's 2 electrons as well. That's kind of the key here. And these electrons are, of course, shared. So the chlorine on the left and the chlorine on the right are both using those electrons. That's how each one of them ends up with 8 valence electrons. These 2 red dots over here only being used by the chlorine on the left. So hopefully that makes sense. Hopefully you've noticed that you already have that down in your notes. Let's move on then. Oh, sorry, before I do that, a triple bond and a double bond. A double bond would have 4 shared electrons because we have 2 lines, so a total of 4 shared electrons. That's how my oxygen has 8. And then for a triple bond, it's 6. 2, 4, 6 total electrons. So each bond still has 2, but then the total now is 6 or 4. So double bonding and triple bonding, that's how we take fewer electrons and we make them still so that each atom has 8. So if we rewind a little bit here, you'll notice that in this situation, I had a total of 12 valence electrons. In this situation with fluorine, I have 14. So with fluorine, I didn't have to share as much as I needed with all oxygen. Because oxygen has a fewer number of total electrons, I need to share more. I need to have double bonds, or in nitrogen's case, over here, I need a triple bond because it has even fewer total electrons. Okay, bottom line is these two rules you should have in your notes. These are true for anything. There's tips and tricks along the ways, but these are the two true facts. The same number of total valence electrons. So for example, in oxygen, we had a total number of 12 valence electrons. 6 dots on each atom, total of 12. And then you need to have stable individual atoms. Each atom needs to have 8 valence electrons. Or if it's hydrogen, they need to have 2 valence electrons. These two facts will always be true as we move forward. And then here are some rules that you probably already also have in your notes. Remember, put the center atom that can form the most number of bonds. So like a carbon, you would never put a hydrogen or a halogen in the middle. You want to give each atom its number of valence electrons, right? You want to put those dots around there. And then you want to start with a single bond. You never want to start with a double bond. A double bond is kind of like, oh, okay, I still need more sharing to go on. Then do a double bond, then do a triple bond. And then always you want to be checking, does it have 8 valence electrons? Yes or no? Okay, here are some examples of practice problems. These practice problems will make you, you'll need to use double and triple bonds for these practice problems. Okay, go ahead and take a moment. You can fast forward through this. I'm just gonna go ahead and actually draw out all these things. So if you want to pause right now, that'd be a good time. Otherwise, you're gonna get some spoilers. And I'm just gonna take some time to draw through these. Great. So right now I'm just giving chlorine its number of valence electrons. Chlorine has 7, silicon's got 4, and phosphorus has 5. Here's SiO2, silicon has 4 again, and oxygen has 6. You'll notice that as I'm putting these dots down, I'm trying to put these dots in strategic places, just so that it makes it easy to kind of connect the dots. You'll also notice that just because I know what the formula is going to look like, I'm going to have an easier time kind of placing these dots because I kind of know where I want them to go. So yeah, the last one I'm getting a little fancy with here, just because I know exactly where I want these dots. Great. Okay, let's start with the first one here. Cl, Si, and P. I put Si in the middle because it's only got 4 valence electrons. Let me just turn this into an I without a dot so that's not confusing. Start with single bonds here. Wabam, wabam. Right away, chlorine over here has 8. 2, 4, 6, and 8. Phosphorus has 1, 2, 3, 4, 5, 6. And silicon also has 6. So both of these have 6. If I form a bond here, they're each going to share 1 electron, so now they both have 7. And then if I do this again, now they both have 8. Pretty awesome, huh? So then what the final answer would look like is it looks something like this. Notice how this triple bond kind of becomes a little bit more condensed than what I currently have. Sorry, a little bit more condensed than what I currently have it. For SiO2, each of my oxygens has 6, and my silicon in the middle here has 4. So I'm going to draw a single bond to start with, kind of connecting these guys up. And now we'll notice that it is 7, 6, and 7. So if I form a double bond over here, now it goes from 6 to 7 and 7 to 8, which is perfect for this oxygen over here. So that worked really well. So why don't I just form another double bond right over here? One thing I want you guys to be careful about though with this drawing here, let me erase this a little bit, is you never want to do what I just did there, where I had 1 dot on top and 1 dot down below. You always want to make sure your dots are in pairs. So your final answer should look something like this here. So dots are always in pairs. It doesn't matter if they're both up top or to the side. It doesn't really matter to me as long as they are pairs. So if you had something like O with 1 dot above it and 1 dot below it, I would actually take points off for that. So make sure that they're both on top. Great, looking at the last one here, this bromine, once again, the dot's a bit out of place. Oops. Okay, well, anyways, The dot's a little bit out of place, so let me just redraw that then. Put one dot there, two dots there, two dots there, two dots there. Our nitrogen looks a little bit like this. One, two. I'm going to draw a double bond here, or two dots here. Then I'm going to put two dots over here. And then for oxygen, it's going to have its two dots, and then two dots. Why not just do that? Okay, so bromine. Draw a bond there. Now it's got 8. And nitrogen, after we draw one bond here, will have 2, 4, 6, 7. Nitrogen's got 7, oxygen's got 2, 4, 6, and 7. So, since they both have 7, the easiest way to turn that into 8 is to form a double bond right here. That's going to give nitrogen an extra electron and oxygen an extra electron. So they both are going to become 8 here. And then we have 2, 4, 6, 8, 2, 4, 6, and 8. So there's the 3 structures right there, kind of what the final answer should look like. So one of the things you'll notice is that I'm very strategic in how I draw dots. At the beginning, you might not be as strategic, which just means you're going to have to erase and redraw. It's not a big deal, but it is helpful to know that you should do this in pencil, just because if you're doing it in pen, you're going to have like marks all over the place, or you're going to, take some shortcuts and maybe not do it the correct way. But part of this process is erasing and redrawing. So if you're doing it on an iPad, it's super nice because you can just erase and redraw like no one's business. Okay, here's a challenging one. This is SO2. So SO2, if you draw it out, it kind of looks something like this. Give yourself a moment, take a crack at this, see if you can't figure this out. Cool, let's go ahead and go over this. So the problem you've probably realized is that first thing you want to do after you give everything its proper number of valence electrons is draw a dot here, a line here between these two dots, and a line here between these two dots. But if you do that, here's what happens. Sulfur's got 8 valence electrons, which is great for sulfur, it's stable, but not great for the oxygens. They both have 7. Now, a lot of kids try to do a lot of different things with this. Kind of the most common incorrect answer is they're like, oh, well, what if we draw a giant bond over here? We don't see that happen. We don't see giant bonds form like from there to there. And realistically, kind of any other thing, like if you draw a bond here, then you have 8, but now sulfur's got 9. If you draw a bond over here, same thing. Sulfur has 9, even though the oxygen has 8. So yeah, you can't just draw a giant bond over here. It would work out. Notice 2, 4, 6, 8 for sulfur, 2, 4, 6, 8, 2, 4, 8. So the confusing thing here is everything's got 8 electrons. Total number of electrons don't change. This technically works according to the Lewis dot structure rules. The unfortunate thing is we don't see this happen in real life. There's something called bond angles, which is just kind of like how close the bonds are and the atoms are to each other. And just because these dots here are super close to these dots, it doesn't happen in real life. It's not what we see. So it's kind of like an exception to the dot and bond rule. The Lewis dot structures is not a perfect metaphor for exactly what happens. So we'd say this is something you can't do. And so kind of here's the rationale that I'll teach you. Here's what I want you to draw in your notes. If you have 2 atoms, here's what happens. Your first atom is your center atom, and your second atom goes to the left, for example, or to the right. Third atom, you could always put that to the right. So if you have 3 atoms, they'll always form a line. That's kind of a true fact. If you have a 4th atom, you could put that on top or below. I'm just going to put it on top. And then if you have a 5th atom, you'll always put it down below. So this is kind of a nice format to remember for all Lewis dot structures. This is always true. Kind of the idea is you always have one atom in the middle, and then depending on how many you have, you can put them on either side first, and then top and bottom second, or top and bottom first and side to side second. But the bottom line is you always have one atom in the middle. So in SO2's case, you couldn't just draw a triangle because that's not what we see actually happens. You'll always have one atom in the middle. I would recreate this on your notes, and then I would also write down this as kind of a third rule of LDS. So always have the same number of total electrons, always have stable individual atoms, and then the third rule is have a center atom. You need to have an atom here in the middle. So make sure you kind of add this third rule to our two, now three rules of Lewis dot structures. Okay, we're going to go back to sulfur dioxide here. Great. Oh, sorry. Before we do that, here's just some examples. Here's an example with 2 atoms. Here's an example of what 3 atoms look like. Here's an example of what 4. Again, it could be top or bottom. And here's an example of what 5 looks like. Notice that I'm kind of using H, which is the simplest atom that can form 1 bond. I'm using O, which is the simplest example that can form 2 bonds, N, the simplest that can form 3, and carbon, the simplest that can form 4. So you could replace fluorine with any halogen or hydrogen. You could replace oxygen with sulfur. You could replace nitrogen with phosphorus, and you could replace carbon with silicon, for example. So between all of those things, you could have a bunch of different combinations. Okay, back to SO2, finally. Here's what I'm going to do, is I'm just going to rearrange dots. Maybe that'll give me some inspiration, is kind of the idea. So we still draw 1 bond, and we're still kind of in the same place as we were before. We've got 7 on oxygen, we've got 7 on the other oxygen, we've got 8 on sulfur. So what I'm going to tell you here is that the bottom line is sulfur has too many electrons. That's the bottom line, right? Because if we draw this second bond, we're sitting at 9 valence electrons for sulfur and 8 valence electrons for oxygen. But wait a minute. If I have 9 valence electrons here on this sulfur and 7 valence electrons on this oxygen, sulfur's got 1 too many and oxygen's got 1 too few. So this is something that happens sometimes, rarely, I would say, is that every once in a while, what you can do is you can actually take an electron from an atom and move it to another atom. And that's what we're actually going to do right here. So here I've kind of rearranged the numbers a little bit. I've moved a little bit of space, and you'll notice that, well, bam, there sulfur transfers its atom over to oxygen. Now sulfur has 2, 4, 6, 8. Oxygen still has 2, 4, 6, 8. And now this oxygen has 2, 4, 6, and 8. So I never changed my number of electrons. I just moved them a little bit. I still have a center atom, and all of my atoms now have 8 valence electrons. This is kind of a weird example, and some chemistry teachers don't like that I teach the electrons move from place to place method. That being said, though, it's kind of hard to explain this because what's really going on has to do with resonance structures and has to do with the fact that, electrons aren't really being held in a line. They're really being, clouds and stuff like that. So it's all kind of complicated. This is just my way of explaining it at an easy level. So yeah, remember, moving electrons, this is what I would write down. Moving electrons is a last resort. And know that there's only 3 problems that we'll give you where you actually have to do this. And there's more complicated stuff happening here. We'll just say you move the electron and it works. Great. We're going to stop there. Tomorrow, what we're going to talk about is drawing polyatomic ions, where based on if you have a charge or not, you actually get to add or remove electrons. Kind of interesting. All right. Thanks for listening, guys. I know this was a long video. We'll see you next time. Take care.